So let me talk about Lab 4 a little. So Lab 3 is not due until tomorrow, right? But I want you to be able to spend time before Tuesday working on the lab. And it's different enough that I want to talk about a few things from here to give you a head start on doing this lab. So this is going to be a more complex circuit, okay? So far you've been designing the traffic controller, but not implementing it, and you've been implementing circuits that you've been given. This one you have to actually design and implement a fairly complex circuit on your own. But it's a fun circuit to work with, okay? It actually does something. It's going to be a 2-bit adder, so it'll add two 2-bit numbers, anything from 0 through 3. So you can go all the way up to 3 plus 3 equals 6, which is pretty cool. Alright, so first experiment is introducing you to the 7-segment display. So you have these on Tinkercad, okay? They have inputs A through G and another input labeled DP. That's for a decimal point. We don't need that. But again, A, B, C, D, E, F, G, those are your 7 inputs. And there's different ways you can configure these, right? Lab 1, you looked at different configurations for different parts of Tinkercad. The 7-segment displays, you can set them up to light up when you connect an input to ground or when you connect an input to power, right? Active low or active high. So the lab tells you how to do that. But basically, your first experiment is you're going to build this circuit, okay? So this circuit basically takes each of the inputs A through G and connects it to a switch. And these switches can be used to run power through any of these LEDs. And then there's a pair of common points that get connected to ground. So you're basically wiring together a whole bunch of little LEDs in this shape, and by flipping the switches you can turn those individual segments on or off. And you can make different letters and numbers out of it. Okay? So first you're going to implement this. And then you're going to wire in this 7-segment display driver. Okay, so I've been calling it a 7447. In Tinkercad, it's the CD4511. It's the same thing as the 7447 that we were just talking about. Okay, 7-segment display driver decoder. So you're going to hook that together, run the simulation, and look at the different input values, right? And observe what's displayed on the display. So that part is you know, building a circuit you're given, doing some experiments, writing down some observations. Okay, experiment 2 takes a big jump, and you're going to design a circuit to do 2-bit addition. So let's talk about how this works. And there's an easy way and a hard way to do this, and we're asking you to do it both ways. Okay, the hard way first, and then the easier way. Not easy, but easier. So what is a 2-bit adder? Well, it's a box. It takes in two 2-bit numbers. So A0, A1, B0, B1. And it should add them together. Well, a 2-bit number looks like this. This corresponds to 0, 1, 2, and 3. So you can add any 2 numbers together where each of those numbers is either 0, 1, 2, or 3, which means your sum can be anything between 0 up through and including 6 if you input 2 3s. So your sum can be as large as 6. You need 3 bits to represent your sum. So we'll call these S0, S1, and S2. So this is a system diagram. We have to say what the inputs and outputs are. So I'm going to say something like this. S equals A plus B. S is S2, S1, S0, where S0 is the least significant bit, okay, the bit on the right. A is equal to A1, A0, where A0 is the least significant bit. And B is B1, B0, where B0 is the least significant bit. So that would be a pretty complete system diagram. Now I haven't explicitly said what a 1 or a 0 means, but we understand that when we're writing this down, we're treating it as an integer, right? Or you could put a sentence in there. But we're turning these inputs A and B into 2-bit integers. We're adding them. We're taking the sum, turning it into a 3-bit integer. But this is still important, right? There's some systems where A1 might be the least significant bit. And so if your input looks like this, what should your sum be? Well, according to this, your sum should be 1 plus 1, which is 2. But if you don't know that A0 is the least significant bit, right, you might be thinking of it like this. Right, in which case this would be 1, 0, 1, 0. It looks like your input is 2 and 2. Maybe your sum is 4. Well, that's a different answer, right? And how do you represent your sum? If your sum is S2, S1, S0, the number 4 looks like this. If your sum is S0, S1, S2, the number 4 looks like that. So how in the world am I going to write a truth table that tells me what S0 should be if I don't even know whether it should be a 1 or a 0 when my inputs are 2? So you got to nail this down, right? This is why the system diagram is the first thing that you need before you get to a truth table, because you've got to be really clear what these inputs are, right? This is the least significant bit, most significant bit. Least, most, least, most. All right, once you've got all of that under control, now you can make a truth table. And so on. Well, this is 0, this is 0. If I add 0 and 0, what should I get? I should get 0, which looks like that. This is 0, this is 1. If I add 0 and 1, I should get a 1, which looks like this. This is 0 and 2. 0 plus 2 is 2, which looks like this. This is 0 and 3. 0 and 3 is 3, which looks like this. Okay, here I've got a 1 and a 0. Those should add together to give me 1. Here's 1 plus 1 is 2. 1 plus 2 is 3. And 1 plus 3 is 4, which looks like that. So now we're using that third output bit. And 8 more rows of inputs and corresponding outputs. Okay, so make the system, describe what you're doing, right? We're making a 2-bit adder. Make the system diagram, make your truth table. Okay, so clearly identified input variables. Okay, that's your system diagram. Write the truth table. And then you're going to minimize this to write in either sum of products or product of sums for each of your outputs. Okay, so you're going to take S2 and you're going to make a K-map. And you're going to fill in all the places where S2 should be a 1, and you're going to cover with rectangles, and you're going to write an equation, and you're going to end up with S2 equals, you know, something plus something plus something. Or if you're doing product of sums, you know, it'll be a product of sums. And then you're going to do the same thing for S1, right? Make a K-map, fill in all the ones from that, cover with rectangles, write the simplified equation, and then do the same thing for S0. You're going to end up with 3 equations. You're going to do it a lot neater than I'm doing it here, okay? Go down the page. Don't do what I do. So write minimized output functions. Okay, this is going to be S2 equals, S1 equals, S0 equals. Clearly state the literal count and corresponding number of gates to implement each of the output functions. Okay, what's a literal count? It's how many things appear in here. So if it turns out S2 equals A1, A0 bar, B1 or B1, A1, B0 bar, or A1 or A0, B0, right? Your literal count is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's the number of terms that appear. Okay, it's just a rough metric of how complex your equation is. So you would say for S2 the literal count is 9, and then how many gates would it take? Well, you're going to need an AND gate, AND gate. You don't need a gate there, you need an AND gate there, so you got 3 ANDs, and then you've got an OR gate. And if you really want to do this analysis, right, what kinds of ANDs? So you need 2 3 input ANDs, 1 2 input and then 1 4 input OR. Okay, that's for S2. Do the same thing for S1, same thing for S0. So you're doing an analysis, okay? And all we've done so far is we've written the truth table for addition, right? This number plus this number is that number. You've done all the work to come up with the simplified equations, and now you're analyzing them. How many terms are in each of those expressions? How many gates do you need? Okay, when you're done with that, you're going to have a big mess. You're going to have something that you really do not want to build. And so step 4 says, using the results from the previous part or your research into possible designs, draw a schematic to implement the 2-bit adder with the carry. And here's the hint. Use full adder and half adder design to simplify and modularize the design. And then use the 7-segment display driver to convert the binary data to 7-segment. You're encouraged to use online research to understand these hints and take advantage of these hints. Okay, so we will let me leave it at there for now. We will talk about these hints on Tuesday, okay? But you should do these first parts of the lab before then, okay? And here's the problem I'm trying to avoid. Anytime that I have taught this, and I've taught this class so many times, anytime that I've gone through lab 4 and we talk about these hints to make your life easier, most students skip these first few steps and they jump straight down to what's called the full adder, half adder design approach. And they end up getting like a 30 out of 100 on the lab because most of the work is up here, okay? And it's really important that you do all of this. This is a straight from the beginning of the course problem for steps 1, 2, and 3. You've got a behavior you want, you write a system diagram, you make a truth table, you write a sum of products from that, you minimize it, okay? So go ahead and do that before Tuesday, and then Tuesday we will talk about this idea of a full adder, half adder, and it's a simpler way to design a 2-bit adder or an n-bit adder, okay? And that's the way that you're going to actually use to implement your circuit in Tinkercad, because the equations you come up with here are going to be really complex. And you can build them in Tinkercad, but it's hard, and it's error prone. And full adder, half adder is a very elegant, very modular design, okay? So we'll leave it at there with steps 1 through 3. Tuesday we'll go through using full adders and half adders to implement a 2-bit adder. But I want to make sure you understand that's not what you're doing up here. Okay, everybody clear on that? All right, So let's move on to the next part of the text. Let's talk about what are called glitches. So far we've been looking at circuits and equations as the same thing. Right? We draw a circuit that does something like this. A goes through an inverter and B goes into an AND gate, and this goes into an OR gate with C, and we get a function f. And we could write f equals C or A bar B. Right? A gets inverted, ANDed with B, that gets ORed with C, that's where f is. And this is the circuit diagram, and this is the Boolean equation, and we could write a truth table. And we've treated these as being the same, right? And typically we start with the truth table, we turn it into an equation, then we turn that into a circuit. The reality is, when you actually get to a physical circuit, you don't have the same thing that you had in the truth table. Physical circuits are imperfect in a number of ways. Now, some of the imperfections we work around, right? The fact that the voltage level coming out of an AND gate that's asserting a logic 1 is not exactly 5 volts, it's probably 4.8 volts. That's okay, because the inputs to our gates don't need to see exactly 5 volts to see a logic 1. So if this is 0.2 volts, and this is, 4.6 volts, well, 0.2 volts, that's not really ground, but it's low enough that the inverter will treat that as being a logic 0, and it will output a logic 1. And it might, output 4.7 volts. And maybe B's coming from another piece of our circuit and it's 4.6 volts. Well, we don't have 5 volts on each of these inputs. But the logic inside this AND gate is set up that it will treat this as a logic 1 and treat this as a logic 1, and it will generate a logic 1, which is, maybe 4.6 volts. And so on. And that's a high enough input that the OR gate will output, a logic 1, which is maybe 4.8 volts. So the fact that we're not getting exactly 5 volts or 0 volts, that's not a problem. Okay, we can manage that with circuitry. But what is a problem is time. And time is where glitches come into play. So let me show you a sample circuit here. So here's an AND gate. And here's a signal A going into my AND gate. And here's A going through an inverter, also going into the AND gate. And here's our output X. And we can analyze this. So I know that if A is coming in here, the output of the inverter is A bar. And so the input to my AND gate is A and A bar. X is equal to A ANDed with A bar. So I can make a truth table. A is either a 0 or a 1. A bar will be the opposite. If I AND these two, I get 0. If I AND these two, I get 0. My output X should just always be a 0. Now this is not a circuit we would typically build, right? Because if we wanted X to be 0, we could just connect it to ground, right? But it's possible that, somewhere in our circuitry is some complex collection of gates that are in effect doing this, right? Under some combination of inputs, we have a value and its inverse going into an AND gate. And we believe that, anything ANDed with its inverse is always going to be 0. But that's not the reality. So let's make something better than a truth table. Let's make what's called a timing diagram. And if you work in digital logic, or if you work in computer science, sooner or later you're going to find yourself staring at a book of timing diagrams for some device that you're working with that's not doing what you wanted. And you're going to be trying to debug it, and it's going to involve staring at these kinds of pictures. Alright, so what is a timing diagram? It's a truth table that's stretched out across time. So we have an axis over here, which shows time. And we have a vertical axis on which we list different variables. For example, our input A, our output of the inverter, A bar, and our output of the circuit, X. So let me call this not A bar. Let me call this, you know, A2, which is equal to A bar, right? But it's the output of an inverter. Alright, so here's what we do. We draw something like an oscilloscope graph. Suppose that our input A is, let's see, suppose that our input A is low. So it's a logic 0. And how do I know if this is high or low? I'm just going to draw a little dotted line here. Just to say, you know, my signal could be here, which is a 1, or here, which is a 0. So A is low. And let's say at some point, A changes to be high, logic 1. And at some other point, it changes back to be a logic 0. Well, let's look at this output of the inverter, A2. And let's go back here to our component specifications and look at a hex inverter. We touched on this the other day. If you scroll down, this is what the thing does in theory. Input's high, output's low, input's low, output is high. So scroll down into the finer print and look for switching characteristics. Okay, so this is done with a supply voltage of 5 volts and room temperature, basically 25 degrees Celsius. And we're looking at the time from an input change to an output change. So T, PLH. This means the propagation delay when the output goes from low to high. And it tells us that it takes 12 nanoseconds for the output to change from low to high. And for the output to change from high to low, it takes 8 nanoseconds. So it's not huge, but there's a little bit of time delay in there, right? Possibly as high as 22 nanoseconds for this direction. So when you change the input of an inverter, the output does not change immediately. It takes a little while. Okay? How long is 12 nanoseconds? Well, a nanosecond is about how far nanosecond is about how long it takes light to travel 1 foot. Okay, so 12 nanoseconds time it takes for light to go, you know, part way across the room. It's a really short period of time, but it's not negligible. All right, so timing diagram. Our input A is low, right? And so the output of the inverter is high. Now at this point in time, and I'm just going to draw a line here to mark this point, our input to the inverter changes from 0 to 1. The output does not change right away. It takes a little while. And then eventually the circuitry inside the inverter catches up and it says, oh yeah, my output should go low now because the input is high. So the output drops. And then over here, the input to the inverter goes low again. And you know, 8, 10, 12 nanoseconds later, the inverter catches up and says, oh yeah, I'm outputting a 1 now. Okay. All right, well, what is X? X is the AND of A and A2. So over here in the beginning, A is 0, A2 is 1, the AND of that is going to be a 0. What happens right here? At this point, both inputs to the inverter are 1. A is a 1, A2 is a 1. When both inputs to an AND gate are 1, what does the output of the AND gate do? It changes to a 1. It takes a little while, there's a propagation delay, but eventually it's going to change to a 1. And then at this point, A2 goes to a 0. So from this point on, the inputs to the AND gate are 1 and 0. Well, that's going to cause the AND gate to go low after a little while. So a little while later, the output will go low. Now, right before this line, the input was 1 and 0. At this point, the input is 0 and 0. 0 and 0 ANDed together, that's still a 0. And then at this point, the inputs become 0 and 1, while 0 ANDed with 1 is still a 1. So that's going to stay as a 0. But there's this little glitch. It's a technical term, right? So the truth table tells us X should always be equal to 0. But under certain circumstances, we can have a few nanoseconds where that output X is not 0, but it's 1. And that can be a problem. Okay, if this is connected to an LED and you expect the LED to stay off, you're not going to notice a 5 or 10 nanosecond ping of the LED, right? That's not going to be a problem. But if this is driving the circuitry that starts the shutdown of the factory, right, at the cost of $25,000, that little 5 or 10 nanosecond glitch might be enough to cause the whole factory to shut down, or a missile to be launched, or the emergency steam release on a nuclear reactor to open up and vent gas into the atmosphere, right? So these glitches, they're very short, but they can be very serious. And they're generally really hard to avoid. I don't know what Tinkercad does with these, so other software you can actually observe these glitches. Somebody asked if Tinkercad, if these happen in Tinkercad. I'm not sure. I don't think there's a way to easily see them because they're so transient. But if you were to hook this up to something that would remember that, I don't know if it'll actually simulate that or not. Be an interesting lab to do sometime. But other software that we use, like the software we'll use later on in this course for FPGAs, will actually catch these. And a lot of the really expensive software that you can buy, you know, the commercial versions of things like Tinkercad, part of why they're so expensive is because they will figure out when there's glitches like this, and they'll represent them and let you work with them. All right, so this is a potential problem, right? And you know, this is a pretty slam dunk circuit, right? A ANDed with A bar is always 0, but there's glitches lurking in there, and they're coming from propagation delays usually, right? Because our truth tables, our Boolean equations don't understand propagation delays, and the simple fact is the time it takes to travel along this path is smaller than the time it takes to travel along this path. And that's one source of why this glitch is happening. So we can study these glitches, and there's material in the book that we're not going to go into that talks about hazards and glitches. You can do some analysis on your circuit and figure out where glitches might possibly occur. And one way to do that is by using a K-map. So take a look at those sections in the book that talk about hazards and glitches. That's potentially useful stuff. But we're not going to use that to deal with glitches. We're going to do something different. So we have a system. We have inputs. And if you see an arrow with a slash through it, it usually means there's more than one arrow, but we're only drawing one arrow. Sometimes you'll see a slash with a 5. That means there's 5 arrows, but we're only drawing one arrow, because too many arrows makes things messy. So this just means I have, you know, one or more inputs, and I have some outputs. And normally, you know, you don't change your inputs, your outputs are stable. The potential for glitches is when one of our inputs changes, it goes high or it goes low. Our output might, you know, change from a 0 to a 1, but it might go through intermediate values along the way. Right? And there's your glitches. So there's ways to deal with this. So one way to deal with this is through some clever software. So we know how to count in binary. Zero, 1, 2, 3, 0, 1, 2, 3. Suppose we have a system that's counting, and it's counting through different steps of a process. Okay, so step 0, step 1, step 2, step 3. And we want these things to happen in a certain order. So say it's a factory system, right? And you have to heat something up and then, you know, turn on some part of the system and then inject it somewhere and then open up something else, right? And they want to go in a certain order. So our step 1, step 0, right, starts off at a 0, 0. S0 is going to change from a 0 to a 1. That's our next step, 1. To get to step 2, two things need to happen. This needs to change from 1 to a 0. This needs to change from a 0 to a 1. Well, if they change at exactly the same moment, we go from 0, 1 to 1, 0. But it's not likely that they're both going to change at exactly the same moment. So here's a more likely scenario. We have 0, 0, we have 0, 1. Suppose this changes to a 0 first, and then this changes to a 1. Okay, we were at a 0, and then a 1, and then a 2, but we briefly went back to step 0. Another possibility, we were at a 0, 0, 0, 1. Maybe this bit changed to a 1 first, and then this lower bit changed to a 0. So we had step 0, step 1, step 2, but we briefly went to step 3 in between. Okay, classic glitch. So here's one way to deal with that. Use a different coding scheme. Let's let 0 be 0, 0, 1 be 0, 1, but let 2 be 1, 1, and 3 be 1, 0. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. And now anytime you move from one step to the next, only a single bit is changing. When we go from step 2 to step 3, just this last bit has to change from a 1 to a 0. Step 1 to step 2, just this bit 1 has to change from a 0 to a 1. And all the way from step 3 to step 0, wow, in our old case, both bits had to change. That could happen in any old crazy order. Here, to change from step 3 to step 0, we just need this most significant bit to change from a 1 to a 0. It might happen in 1 nanosecond, 5 nanoseconds, 7 nanoseconds, but it does not matter. It's going to be in this state for a while, and then it's going to be in that state, with no glitchy intermediate state. So this is a useful order for counting. Now we can't just add up powers of 2 to get 0, 1, 2, or 3, but it's still a valid way to assign a binary code to each of our steps. So this is something called a gray code. And there's how we count in 2-bit gray code. I never know if it's an AY or an EY. And, you know, not coincidentally, this is the order in which we label the sides of our K-map. Why? Because when we do our K-maps, what we want is we want one of our input bits to change as we move from one square to an adjacent square. And it's the same thing as avoiding glitches here. So all this stuff is tied into everything else. Okay, this is also called a reflective gray code. And why is that? Well, remember when we're trying to write numbers in binary, there's a trick we can use. So forget gray code for a minute, right? Just straight binary. Here's how we write 2-bit numbers in sequence. If you want to write 3-bit numbers, what do? Take this pattern you just wrote, replicate it, and put zeros in front of the top 4 and put 1s in front of the bottom 4. And there's our 3-bit counting sequence. And if you want to count 4-bit numbers, take this whole pattern, replicate it again, and put zeros on top of the front half, and put 1s in front of the bottom half. And there's your 4-bit counting sequence. Okay, when we work with gray code or reflective gray code, we do something almost exactly the same. But to go from 2 bits to 3 bits, instead of copying this down here, we reflect it. Okay, so this is our 2-bit gray code. We're going to take this, but we're going to flip it over. So you're going to write down 1 0 1 1 0 1 0 0. And we're going to put zeros in front of the ones on top and 1s in front of the ones on bottom. There's your 3-bit gray code. And again, anytime you move from one entry to the next, a single bit will change. And then if you want 4-bit gray code, take this and reflect it. Put zeros in front of the top half and put 1s in front of the bottom half. And there's your 4-bit gray code, and so on. So that's one way we deal with glitches sometimes. When we talk about state machines in another week or two, we'll talk about using gray codes to avoid glitches in our states. So this is commonly used. But it doesn't get us all the way where we're trying to go. There's still situations where we're going to have circuits that aren't necessarily counting, but are doing things that end up being dependent on how long it takes logic gates to respond to their inputs. And that's just really hard to manage. So the way we've dealt with this for decades is we introduce a clock. And here's the idea. We have a circuit with some inputs and some outputs. And when inputs change, the outputs will bounce around. They'll go high, they'll go low, they'll move around to different values. But eventually they will stabilize. Okay? The idea is if you have a circuit like the circuits we've been building, for a fixed set of inputs, you can define what the outputs will be based on truth tables. They don't change. But it may take a while for them to get to those stable values because of the realities of physical chips. But at some point, you know, if the inputs haven't changed for a while, the outputs will be rock solid. So the idea is we're going to introduce a clock into our systems. And every time this clock ticks, inputs are going to change. And as soon as those inputs change, outputs might start to change. And temporary values in between the inputs and the outputs might start to change. And things might get glitchy and you might get a bunch of noise. But eventually things will settle down. And they should settle down before the next clock tick. So that when the clock ticks, we know that all the outputs we're looking at that moment are valid. And the idea is we only pay attention to things when the clock ticks, not in between. So clock ticks, things move around, things change, everything stabilizes. Clock ticks, we look at the new values of the outputs. That changes more inputs, things move around, they're unstable, they bounce, eventually they stabilize. Next clock tick, and on, and on, and on. So this is called synchronous logic. And this is how almost all of our computer and computer-related systems are built. They contain clocks. And the clocks basically say, I don't care what happens in between the clock ticks, but when my clock ticks, I want everything to be in order. Right? So things can move around, things can change value, but on the clock tick, everything should have stabilized by then. So when you buy a PC, and it says, it's got a 3.2 gigahertz clock, that's how fast these ticks are happening. 3.2 billion times per second. And the hardware inside is fast enough that when the input to a circuit changes, everything that needs to change in response to that will happen within 3.2 billionth of a second. So how many people here have played around with overclocking? Right, you get a CPU and it runs at 3.2 gigahertz. Well, maybe we can run it a little faster, right? These clocks are software controllable. So you can, by just writing code, right? Yay, we've got overclockers. By just writing code, you can make this clock run faster. Well, what if it runs at 3.21 gigahertz? That's, 1/3 of a percent faster. Well, when you get a system with a 3.2 gigahertz clock, so these things are coming out 3.2 billion times a second, it's a really good bet that things are stable pretty far before this clock tick. It would be a dangerous design to say, I'm going to let changes happen right up to here, and then everything's going to be stable. Because, you run it in a hotter room in the middle of summer, and circuitry might run at a different speed. You run it in winter, it might go slower. So there's always a margin of safety, and chances are if you have a 3.2 gigahertz system, your inputs are stable, maybe this far before the clock tick. Which means maybe I can make my clock tick after this much time instead of that much time. That's a faster clock. So maybe if I set my clock to 3.21 gigahertz, my system will still work and it'll be faster. Maybe I can set it to 3.3 gigahertz. Maybe I can set it to 4 gigahertz. Okay. There's two reasons that this voids your warranty when you do this. One, because sooner or later your clock is going to change faster than the circuitry has had time to stabilize. And now you have effectively random code running in your system. And you can do all kinds of physical damage to hardware through software. Okay, especially if you have things like programmable elements inside and so on and so forth. The other problem is the faster your clock runs, the hotter your circuitry becomes. Because these are physical devices, they give off heat. And the faster you clock, the more heat they give off. So all of the cooling systems that you have in your laptop or your desktop, all of the fans and the ducting that's in there, and if you have a really fast system, you have like water flowing through it, or maybe Freon or something, that's all to wick away the heat that comes from the fact that you have a clock ticking 3 billion times a second, and you might have 1 billion transistors responding to that. right? 1 billion transistors changing state 3 billion times a second. It's a lot of heat. Yeah, and somebody points out they have an i5 rated at 2.7 gigahertz, but it runs at 3.2 without overclocking. So, you know, there's different ways to do this. And sometimes, you know, a 3.2 gigahertz processor that gets manufactured, when they test it, it only runs at 2.8 gigahertz. Well, they'll repackage it and sell it as a 2.8 gig processor. It might be the same physical stuff inside, but the way it was manufactured, it just doesn't run reliably as fast. And sometimes, you know, a system is rated at 2.7, but under certain conditions, it's known that it can run faster and the system will adopt the clocks. Yeah, silicon lottery, right? So the glitchiness is one issue. The bigger issue is heat, right? And so when you see people overclocking, or if you've overclocked, or if you look at videos, there's always extreme cooling around these things, right? Sometimes they actually soak them in something like liquid nitrogen, or Freon. Nitrogen's too cold. But you know, you have to cool this thing down to deal with the heat, and eventually the heat gets away from you, and you can smoke your processor, right? You can cause it to burn itself up and give off smoke, and in some extreme cases catch on fire, right? Just by running the clock too fast. Because these are all little, you know, heating elements inside, right? Wire, what's a toaster? It's wire that you push a lot of current through. Well, if you overclocked your CPU, it's the same thing. You're pushing more and more current faster through the wires before it can dissipate the heat. You've got a little toasting system in there. You can literally cook your chip. But anyway, if we stay away from the overclocking thing, right? Clocking is the way that we deal with glitches. And so we're going to move towards working with clocked systems, and we're going to be working with memory systems. Okay? So systems that, as I mentioned last Thursday, that understand what's happened to them in the past and respond to that. Okay, so this takes us to sequential circuits, which was where we left off last week. And I left you with this idea of a circuit built like this. And the observation that if this output was a 1, that 1 would feed the inverter to become a 0, the 0 would feed this inverter to become a 1, and it would stay a 1. But if the output happened to be a 0, that 0 will feed this inverter output a 1, will feed this inverter output a 0, it will stay a 0. So this can store a bit, it can remember a value. And you know, if we were to take this output and just temporarily touch it to 5 volts to force this to a 1, and then take away that wire that touched it to 5 volts, this 1 will become a 0, will become a 1. This thing will remember that value 1. And if I take a wire connected to ground and just touch it to that output for a moment, this will go to a 0, this will be a 1, a 0, a 1, this will stay a 0. So this simple circuit can remember what the voltage was the last time you touched this to a voltage, either 5 volts or 0 volts. Okay, it's got a memory of the past. But that's not a good way to build a memory element, because if this inverter is trying to output a 0, and I temporarily connect this to 5 volts, I'm creating a short. Okay, I'm taking this circuitry in here and I'm forcing it to connect to 5 volts. So yeah, so we're going to do this with a logic gate instead of an inverter. And it's not going to be an AND gate, it's going to be a NAND gate, or a NOR gate. So let me show you a slightly different version of this circuit, which is a pair of NAND gates. And remember, NANDs are almost like inverters. I should have drawn this on the bottom. Alright, Alright, so here's an output X. And let's remind ourselves what a NAND gate looks like. So it does that. Well, we can think of a NAND gate differently, right? We can also think of it as if B equals 0, then the NAND gate is always outputting a 1. If B equals 1, then the NAND gate is outputting the opposite of A. So we can make these things act like inverters by putting a 1 into one of the inputs. So let me call this input S bar, and let me call this input R bar. And let's look at what this circuit does. So suppose I set S bar to a 0. I've got a 0 going in here. Well, if one of my inputs to my NAND gate is 0, the output is 1. So my X is going to be 1. Doesn't really matter what happens back here. It doesn't matter what the value of R bar is. Doesn't matter what the output here is. If S bar is 0, then the output of this gate is going to be 1. On the other hand, if S bar is a 1, right, then my NAND gate is just acting like an inverter. But if my R bar is a 0, right, if one of my inputs is 0, the output of the NAND here will be a 1. That 1 will get inverted. X will be a 0. But if S bar and R bar are both 1, if that's a 1 and that's a 1, then each of these is acting like an inverter, and this is really just this circuit. Which means it's going to remember whatever its current value is. So now I have a circuit. X is some particular value. If I take this input and I pull it low for a moment, my output will go high. If I return this back to not being pulled low, if I pull it high again, then my output will be whatever its value was, which was 1. Now if I take this input and I pull it low, my output will go low. And when I pull this high again, my output will stay low. So this is a full-blown memory circuit. I can force the output to be low by pulling this low and then pulling it back high. Or I can force it high by pulling this low and letting it go back high. And so the normal state of this device is to have both my inputs high, and X will be whatever X was a moment ago. But I can set the output by pulling the set line low. I can reset the output by pulling the reset line low. Okay, so this is something called an SR latch. So we will start talking about those more next week, and that's going to be where we get into memory circuits and sequential circuits. All right, we are out of time. Keep working away on Lab 3. Let me know if you have questions, and take a start on Lab 4. Have a great rest of the day, great week. I will see you next time.
Thank you.
Thank you.